Well, good afternoon, physical science students. I hope everyone is well. I'm doing well. I'm in very hot and humid Upper Marlboro, Maryland, and I will hopefully be back on Wednesday so you don't have to watch my virtual lessons for too long. Although I think it is a good experience to maybe do what some other students are doing at this time, and that is learning virtually. And so hopefully you will have a little bit of understanding, at least, of the things that we are doing in our classes today. I do encourage you to listen carefully, because physical science is one of those sciences that is going to get tough fast. And today is going to be a great example of getting tough really fast. Unfortunately, I'm not here with you to celebrate chapter number 2, which is usually the start of people's doom in physical science. So I do encourage you to listen very carefully. Now at this time, I would like those of you who did not take the chapter 1 test, okay, to be thinking in your minds, when am I taking the test? Now, the soonest opportunity will be upon my return on Wednesday, and I would like you to take it on Wednesday. If at all possible, you can take it on Wednesday. And that way we don't endlessly get behind. That would be one of the worst things for you to do. But if you did take the test, your test will be on the desk. In the pile of physical science stuff, it'll say science, matter, and energy. And your substitute should be making her way over there to grab your test. Now, she does not know your names, so you're going to have to respond to her as she's passing out the test. And all we are going to be doing now is taking a look at the grade. Unfortunately, we can't really go over the test because you're going to have people in here that have not taken the test, and I don't have an answer key for her, and she does not know all of the answers off the top of her head. So at this time, I would like the video to be paused and for you to be able to see your test grade. Alright, I'm assuming that your teacher has paused this video, and we are going to be getting into chapter 2, measuring matter. And unfortunately, I have been extremely hasty in how I had to leave on Friday, and it completely slipped my mind. At least I think it completely slipped my mind to print out your notes for this chapter. Now, your substitute is welcome to look for your notes, but I think I forgot. And if that's the case, unfortunately, I'm going to have to teach anyway. So you're going to have to actually open up your textbook like they did that in the days of old, and open to page 22. I promise that we will be working with notes at some point upon my return on Wednesday, and I will hopefully be able to clarify everything at that point. But you are going to be taking a look at page 22, and on the off chance that I did print the notes, which I don't think I did, your teacher can of course pass them out and pause the video again. But we are on section 2.1, page 22, and we are on the chapter measuring matter. And we have this incredible quote from Galileo, which says, "Science is written in the great book of the universe, which lies always open. But we must first understand the language and the character in which it is written. That language is mathematics. Its characters are triangles, circles, and other geometric figures without which we cannot understand and wander aimlessly through a dark labyrinth. I love that word labyrinth. It means maze, where you just get confused. Now, science would be confusing without a thorough understanding of mathematics, and I love math, and I have to in order to teach science. And I hope you do too, or else this chapter might get difficult. Now, you do see on page number 22, the language of science is going to be mathematics. And you see that in the italics on page 22. The physical sciences are inseparable from mathematics, the language of science. Mathematics is the science of quantity, or quantifying things, science of numbers. And there are some other sciences that deal with qualitative relationships, or descriptions, as we see on this next page. Now, descriptions are important. And sometimes in science, you can only describe instead of mathematically quantify. For instance, you take a look at that bird over there, and of course you could mathematically quantify its height, or its weight, or, its beak strength. But there's some things you can't quantify, and you'd have to describe it thoroughly. For instance, color. You'd have to describe its bluish, purplish, whitish appearance through a very deep description, just simply because you can't necessarily take a picture of it. Technology, it really builds on these quantitative and qualitative descriptions, allowing us to do some really cool stuff, and have really cool stuff. And you see on page 23 an equation, a set of symbols which describe a relationship. Now, over your years, you've probably memorized several equations. For instance, in this equation, volume equals length times width times height. And you see in this diagram here, 4 times 12 is 48. 48 times 3, I believe, is 144. And that's just off the top of my head. So, in this case, an equal sign symbolizes that this side of the equation and this side of the equation are equivalent, or they are equal to each other. Volume is indeed the sum, or the product of length times width times height. And you can see how we can also rearrange an equation. Now, a lot of people don't like to do this, but you have this equation, speed equals distance multiplied or divided by time. I'll write this out here in a way that we generally understand. Distance divided by time. But as it turns out, this is not the only way to portray this equation. Because in mathematics, we have this principle that we can multiply both sides by something to cancel it on one side and to get it on the other side. For instance, if you multiply this side by t, and you multiply this side by t, you get that time times speed equals, and these two cancel out, distance. And you can actually divide by speed to get an equation. Time equals distance divided by speed. Now, that's not the original way that it was written. Speed equals distance divided by time. But this here is a legitimate equation. And it is legitimate mathematically and algebraically. And we can rearrange an equation for whatever use we'd like. And you can see that in table 2.1. And we can arrange whatever equation we would like, as long as we do it mathematically in a way that is appropriate algebraically. Now, as we move on to page 24, we see this interesting sequence. It's called the Fibonacci sequence. Now, maybe you've heard of this. And a sequence is anything really that has an order to it. And the Fibonacci sequence does have an order. 0 plus 1 is 1. And then you take these two numbers and you add them together. 1 plus 1 equals 2. And you take these two numbers and add them together. 1 plus 2 equals 3. And I'm hoping you're getting the idea. You take 2 and 3 together. 2 plus 3 equals 5. And then 3 and 5 is 8. And then 5 plus 8 is 13. 8 plus 13 is 21. And this Fibonacci sequence is a sequence found all over biology and astronomy, among other things. For instance, the Fibonacci sequence is the basis of the spiral galaxy. Fibonacci sequence is the basis of many meteorological phenomena like the hurricane. The Fibonacci sequence applies to flowers. It applies to the shell of a lot of snails and such things. And you can see the nautilus shell on page 24, the pineapple. And really this is incredible. It points to a creator god, and it has to, because a random chaotic universe like evolution and the Big Bang Theory describe would not have such really intricate mathematical details. It's God's signature in what he does as an amazing creator. He didn't have to make spiral galaxies that followed mathematical sequences, but he did. And he did that really to glorify himself. And for us to just look at him and say, wow, before we even discovered the Fibonacci sequence, God was here, and we were not even close. The next thing is accuracy and precision. Now, I've given a pretty nifty diagram here. You can see one in your book on page 25. Accuracy is how close a measurement reflects an actual value. Precision is how close measurements are to each other. So this person here would be accurate and precise. This person here would not be accurate. They didn't hit the bullseye. But they were precise because all of their bullets or whatever they used are in the same place. This would be like a thermometer that reads 3 degrees low, but it reads 3 degrees low every single time. So it's pretty reliably inaccurate, if that makes sense. This is not precise, but it is pretty accurate. This person is shooting around the target and getting pretty close to the center, but not close to where they've shot each time. This is not accurate, nor is it precise. The bullets kind of spread out everywhere over this target. And of course in science we would like to be both accurate and precise. We'd like our measurement to be the actual value, and for it to be the actual value every single time we take a measurement. Now, if you would like to turn to page 26, I'm about to hurt you. Your mind. Terrible. Something called significant figures. Now, you might think to yourself after this lesson is done, how on earth is this useful? And it's a legitimate question with a legitimate answer because it is. It just takes a long time to see its usefulness. Now take a look at this picture. Okay, this is of a political rally somewhere in the state of Michigan. I don't know who they're representing, but there's a lot of people there, so I'm assuming it's probably a president, but I digress. You go to a political rally, how many people do you think are there? Now I look at that picture and I'm going to guess 6,000. Okay. I'm going to write that down, 6,000. Maybe I'm wrong, maybe I'm right, doesn't really matter. It's a guess, right? Now, you and your friend get led into the political rally. And let's say you bring another friend. You bring 3 people. How many people are at that political rally now? Now, if you said there's 6,003, you are incorrect. The reason is because your first number is a complete guess. So it wouldn't be right to say 6,003. That's an exact number. 6,003. You know, that's something that's really specific. The 3 would not affect your original estimate. It would still be about 6,000 people, more or less. Okay? You wouldn't say 6,003. You know, same thing if we were, let's say we were talking about bales of hay. And a farmer looks out into his field and he says, I got about 10,000 bales of hay out there. And you say, well, I got one in the back of my pickup truck. How many does that make? It'd still be about 10,000. Now, if the farmer knew exactly how many he had 10,000. Then if you brought one to him, it would be about 10,001. But right here we're talking about guessing. And when you guess, smaller amounts don't really affect the total in your guess. And there's a really strategic way to approach this. And we approach it using significant figures. And significant figures really has 4 rules. Your textbook has 5 rules. And I kind of summarize these rules differently than your textbook. And that's okay, because your textbook does a great job too. Both are correct. Okay? And a significant figure only records what is certain with one uncertain place. So, if I go measure myself, I measure my weight, and I am 50.45 kilograms. This last number is uncertain. It is a guess. Therefore, the hundredths place can be significant, but the thousandths place is not. You don't guess after your guess. You don't say 4, 5, 2, 2, 3, 6, 7, 4, whatever. You don't guess after your guess. You know, if I picked up a bag and I said it was about 10 pounds, I wouldn't say it's 10.0 pounds. No, it's a guess. I just say 10 pounds. I wouldn't say 10.05792 pounds. They think I'm crazy. Your guess is a guess. And here's the significant figure rules. You count all non-zeros. You do not count zeros to the left of non-zeros. For instance, 0.0038 only has 2 significant figures, the 3 and the 8. These zeros here, they are simply placeholders. They hold the thousandths place for the 3. We could rewrite that using scientific notation and get rid of those zeros completely. Zeros between non-zeros are significant, 2,077. Now, if I said I have $2,077 on me, that zero is important. It's not like you can get rid of the zero and say I have 277. That'd be terrible. I want my thousands. But it's not like we can replace that with another non-zero like 1 or 2, because that's a specific number, 2007. And so that zero between non-zeros is significant. And any zero that is followed by a decimal is significant. And so this 40,350 dot is significant. If it did not have the dot, the 0 would not be significant. And you can see that on number 4. 10.000, all zeros are significant. And that is because there is a dot, which or that decimal, which signifies that the ones place is significant, and when you add in a whole bunch of zeros after the decimal, it's showing the specificity, or how specific the estimate is. I have about 10.000 pounds of stuff. Well, you'd only add those zeros in if they were important. Now, this is where it gets difficult. You have some practice. Okay, 3.14 has 1, 2, 3 non-zeros and 3 significant figures. 1770 has 1, 2, 3 non-zeros. They're all significant. And this 0 is insignificant. The reason being is because it does not have a decimal after it. So there is only 3 significant figures here. Now, all these zeros in this third example, 0.000001, all these zeros are insignificant because they're all placeholders. Placeholder for the 10th place, 100th place, 1000th place, 10,000, 100,000, millionths place, and the 10 millionths place has this 1. Therefore, there is 1 significant figure. This one here, 2,000. The 2, of course, is significant because it is a non-zero, but look at this decimal. This number is an exact number. 2,000 exactly. It has 4 significant figures. But this one does not have the decimal. So the only non-zero is 1. Therefore, there is only 1 significant figure in that answer. Now, before you hate me, let's take a look at example 2.1. I'm just going to go back so you don't even have to look at that page yet. Example 2.1 on page 26, they give you a couple of numbers. 811, 3 significant figures. All 3 numbers are non-zeros. Letter B, 3 significant figures, because the zeros are just placeholders for the tenths and for the ones place. 3046, 4 significant figures, because the 0 is found between the 3 and the 4. Can't just get rid of it, or it would change the meaning completely. Letter D, 3 significant figures, because the 0 is in between non-zeros, 3 and 5. 40.0 has 3 significant figures because of the decimal, and you wouldn't add numbers after the decimal unless they were important. Letter F, 40 has 1 significant figure. It is a guess because that decimal is not present. And letter G, 40 dot, has 2 significant figures. That 40 is significant. It is, or that 0 is significant. It says it is exactly 40, instead of an approximately 40. And there's a big difference between approximate and exactly. There are 40 students on this campus. That is an exact number. Instead of, well, how many after kids are there? Aftercare kids are there? I don't know, maybe 40, a little more, a little less. That's an estimate. You would not put you would not put a decimal in that instance. Now, hopefully I haven't fried your brain too much. But there is more to this, and I'm going to introduce it today, but we won't get too far into it. Okay? And that is addition and subtraction, multiplication, division of significant figures. Okay, and I'm just going to explain the reasoning behind this, and we're actually going to get to the actual examples tomorrow. Now, let's say you and your friend, for whatever reason, you were adding the weights of your lunch boxes. Why? I don't know, but you are. And your friend, they used a extremely scientific, very specific scale used by engineers, and they got an exact weight of 6.022 pounds. And you instead went home to your bathroom and chucked it on the bathroom scale and got 7. And your friend says, well, let's add the lunch weights together. It turns out that the answer has to be rounded to the ones place because your only significant figure is in the ones place. Your answer has to be rounded to the ones place. Okay? And it can't be 13.022 because this here is a guess. And the guess stops at the ones place. So your answer has to stop at the ones place too. Another example would maybe be with money. You know, maybe you go up to your friend and you say, well, how much money do you have for your Xbox? And your friend says, well, my parents gave me $200. What nice parents, right? And you go to them and you say, well, I have $94.77. Now, this $200 is going to be an estimate because there's no dot here. Remember, your friend said, I have about $200. And so while you can add these together and get 294.77, you actually have to round to the only place that is significant in this top portion, and that's the hundreds place. Your answer has to be rounded to the hundreds place. And you have to estimate that your combined net worth is about $300. And I know that's kind of annoying, but it's how scientists have to do their work. Now, when you do multiplication and division, you have to round not to the place value, like the hundredths, the tens, the ones place. You actually round to, and forgive my voice is gone. You actually have to round to how many significant figures something has. So this is 3 significant figures. This is 1. So your answer may only have 1 significant figure. You go with the least of the 2. Now, why is that important? Well, let's say you're working on the farm again, and your friend looks at you and they say, well, I have 687 cows. A lot of cows, right? And you go up to them and you say, well, I bet you I have somewhere around double the cows. And you can double these numbers and, you can get a very exact number. And that is 1,374. But this number here, 2, is a rough double. Oops. Auto update. Microsoft, get out of here. Alright. It's a rough double. It's not an exact double. Okay. If it was an exact double, we'd do something a little different. But a rough double, you said, I have about that many, so let's double it. Your answer can only have one significant figure. And so your answer here is not 1,374. Your answer would be approximately 1,000. Because 1,000 has one significant figure. Now if you're thinking to yourself, well, that's stupid. Why can't we say exactly? The reason is because scientists have to work. They have to work in significant figures, because if they get too specific with their range, they can really get themselves into trouble. You know, and they could say, you know, maybe something that could get somebody hurt. Everything is an estimate. You ever see this symbol? Okay. This is a symbol which means plus or minus. Everything has that. You look on your bag of potato chips, and it'll say something like, it's 13 ounces. Plus or minus, about an ounce. What does that mean? They let you buy potato chips that are somewhere around 13 ounces. But the weight kind of varies. Could be 12, could be 14, could be 12.25. But it's pretty close to 13. Nothing is exact. When you take medicine, like acetaminophen, you might take 200 milligrams. Well, it's not exactly 200. It might be 199.42 or 201.87. Which is why we need significant figures. Because even the best scientists have to round. And with that, I don't want to fry your brains anymore. I will do the rest tomorrow. I will remind you of something very important tomorrow, and that is your quiz. You do have a quiz tomorrow. And your quiz is going to be over the stuff you learned today. So, if you didn't get these ideas with significant figures, I would highly recommend you invest yourself on page 26, because it will be about half your quiz tomorrow. And that quiz will be very telling who gets this and who doesn't. Maybe ask a friend who thinks they understand. And I will hopefully be there to clarify later on as we learn together what it means to round properly and use scientific notation in physical science. If you have any time left, I welcome you to study these rules with a friend and to maybe get some work completed ahead of time in your section review 2.1. Alright, I'm signing off for the day, and you guys have a wonderful rest of your Monday.